Hi, my name is Martina, and I will present the paper Searching for Search Errors in Neural Morphological Inflection. This is joint work with Clara, Meister, and Cotterell. Machine translation is the task of translating a sentence in the source language into a sentence in the target language. Today, the predominant choice for modeling this task is neural networks. In particular, sequence-to-sequence models, which can transform one sequence into another sequence. This class of models typically has an encoder-decoder architecture. The encoder encodes the input sequence into an internal representation, and from that, the decoder generates the output sequence. There are different architecture options for the encoder and decoder, for example, the RNN or transformer architecture. A sequence-to-sequence model essentially models the probability of output sequence Y given input sequence X. The idea is that the model should assign a high probability to an output sequence Y if Y is actually the correct solution. However, there's a problem with this type of architecture. Intuitively, you would expect that increasing the beam size should lead to better solutions because you inspect a larger portion of the search space. However, this is not the case for some word-level tasks, for example, machine translation. In fact, the blue score starts to decrease after a beam size of around 5. In experiments by Stolberg and Byrne, for more than 50% of the translations, the empty string was actually the output sequence with the highest probability under the model. These cases where the decoding strategy does not find the global optimum under the model are called search errors. Despite these shortcomings, sequence-to-sequence models are used for a wide range of tasks, for instance, also for abstractive summarization and morphological inflection generation. Morphological inflection generation is different from these other two tasks in a number of aspects. It consists of generating the correct word form given a lemma and a set of morphological tags. The evaluation metric for morphological inflection is prediction accuracy. There are a number of differences to machine translation. For instance, morphological inflection is modeled on a character level, while machine translation is typically modeled on a word or subword level. As a result, the vocabulary is smaller for morphological inflection, as it only consists of the single characters of the alphabet, while for machine translation, it often includes a large number of words and subwords. Also, the sequences are shorter. Those two things together imply that the output space is much smaller for morphological inflection. Another difference is ambiguity. For a given sentence, there are often several equally correct translations. In contrast, there is usually only one correct inflection given a lemma and a set of morphological tags. Those things combined may suggest that morphological inflection is easier than machine translation. So, should we expect poor calibration in morphological inflectors? On one hand, we could think the answer is yes, because the same sequence-to-sequence architecture is used as in machine translation, so we could expect the same shortcomings. On the other hand, the task of morphological inflection might be easier than machine translation, so it could also be possible that those models actually calibrate well. This leads us to our scientific question. Do state-of-the-art morphological inflectors suffer from poor calibration? We ran morphological inflection experiments along these three experimental axes. As models, we used a transformer and a neuralized hidden Markov model. We used the data from the SIGMorphon 2020 shared task, which includes morphological inflection data for 90 languages. Then we decoded applying different decoding strategies: beam search with increasing beam sizes k, and exact search with Dijkstra's algorithm. The first question we wanted to answer was to what extent performance, that is, accuracy, degrades for larger beam sizes when decoding with beam search. We found that it doesn't. For both models, there's barely a difference in accuracy when increasing the beam size, even compared to exact search. How often is the empty string the global optimum? Overall, the empty string was the global optimum in only 2% of the cases for the HMM and 0% for the transformer, where we didn't observe any empty strings. We also explored if there are differences for low resource and high resource settings. Indeed, for low resource settings, the empty string was the global optimum more often, in 8% of the cases for the HMM. For high resource languages, we barely found any empty strings. We also investigated how far apart the log probability of the chosen solution and the log probability of the empty string lie from each other. We wanted to get an intuition as to whether these models are poorly calibrated, like those in neural machine translation often are. Overall, we found the difference between these probabilities to be quite large. When looking at the log probability of the empty string by resource groups for the HMM, we see that the probability of the empty string is higher if there are few training samples available. In particular, there are two outliers where the probability of the empty string is even higher. One of them is the Zarma language. It is actually extremely low resource. There were only 56 training samples. For this language, we observed that the log probability of the empty string and the log probability of the chosen solution were indeed very close together. And in 81% of the cases, the empty string was actually the global optimum. Last but not least, how many search errors are there when decoding with beam search using different beam sizes? We can see that for both models, there are only very few search errors. Greedy search very often finds the global optimum, in 94% of the cases for the HMM and 99% for the transformer. So, to sum up, we investigated whether neural sequence-to-sequence models are poorly calibrated on the task of morphological inflection generation. We found that these models are very well calibrated. Moreover, greedy search often finds the global optimum. The few search errors that we observed were mostly in low resource settings, which is also where the empty string often had higher probability under the model. We speculate that the poor calibration in the case of machine translation may not result from the nature of sequence-to-sequence models for language generation, but may stem from characteristics of the task itself. Thank you for listening. For more details, here's a link to our paper.